Okay, so here's a couple more complicated series to consider. All right, and I'm going to take this one first. So in this example, let's imagine you're working through a homework set in the section on ratio tests. So you're just applying ratio test everywhere. And so you try applying ratio test to this series right here. So imagine that scenario. So we take the limit as n approaches infinity again of the n plus 1 term over the nth term. So in this case, that's the limit as n approaches infinity of the absolute value of the n plus 1 term. So make all of these n's n plus 1s for a n plus 1 here. So this will be negative 1 to the n plus 1 times n plus 1 plus 2. I'm going to start writing some of this in black here. So the n plus 1 plus 2 over n plus 1 in place of this n, and then n plus 1 plus 1. There. So there's your a n plus 1. Over a n, but if it's okay with you guys, at this point, I'm going to, instead of dividing by a n, instead of dividing by another fraction, I'm going to go ahead and multiply by the reciprocal. And so with the nth term, you just write what you see, but I'm going to put the reciprocal. So n times n plus 1 over negative 1 to the n times n plus 2. Okay, and now I want to think about the absolute value. So negative 1 to the n plus 1 is either negative 1 or positive 1, right? Depending on if the power is even or odd. If it's an even power, it's positive 1. Odd power, it's negative 1. Either way, you take the absolute value of this guy and it's 1. Same thing down here. So yeah, I mean, I'm aware I could cancel the negative 1 to the n, but really, if it's going inside an absolute value, you don't even need to write the powers of negative 1, because the absolute value of negative 1 to the n, or negative 1 to the n plus 1, the absolute value of power of negative 1 is going to be 1 in these instances. So you could just skip it altogether, your negative 1 to the n's, if you're applying the ratio test or the root test, so it's going inside an absolute value. But here I canceled it. I've got negative 1 to the first, which if I take the absolute value, that's just 1. So I'm going to drop that part of that expression. Everything else is positive, because n is assumed to be a positive integer throughout this chapter. So I'm going to drop the absolute value now, because I took the absolute value. This is 1. Absolute value of everything else is exactly what we see. So this is n plus 3 times n plus 1. I'm just writing down what's left and cleaning it up a bit. And then so we've got n plus 1 times this is n plus 2 times another n plus 2 over here, right? So I might as well cancel these n plus 1s. Say I multiply out what's left. So the numerator here, if I distribute this n, the numerator is n squared plus 3n. The denominator is n plus 2 times n plus 2. So that's n squared plus 4n plus 4. Notice, again, same degree in the numerator and denominator. So the limit is the ratio of the leading coefficients, which is 1 over 1. So the limit here is 1. And that's bad news with the ratio test. So when the limit is 1, ratio test is inconclusive. Ratio test inconclusive here. And you'll have to go back and try another test. Now, when I take a step back, you should be thinking, oh yeah, well, why was I even doing the ratio test in the first place? Ratio test works best with factorial expressions. It also works well with nth powers. Rational expressions like this typically are going to give you a limit that's 1. So you don't really, in the future, I mean, I made the mistake for you, so you don't have to make this mistake in your homework. You don't want to use ratio test for a series of this form, for a rational expression, polynomial or polynomial, because typically it's going to give you a limit that's 1, so it's inconclusive. It was a waste of time. Not a waste of time. I mean, I wanted to show you guys what it looks like when you run into this inconclusive scenario. But okay, so we have to go back to the drawing board and think of a different test. What should we have applied to this series? Well, it's an alternating series, right? The negative 1 to the n is the giveaway there. So we could use the alternating series test. That's a nice quick test to use, usually. So if we try alternating series test, AST, because we see this negative 1 to the n, then remember with alternating series test, you check two conditions. One is the limit of the non-alternating part of this, which is everything except for the negative 1 to the n, is that limit 0? Okay, so in this case, the limit, the non-alternating part would be, like I said, everything except for that negative 1 to the n. So it'd be this. Now you've got a rational expression with a greater degree in the denominator. This is n squared plus n if I multiply it out into the first and the numerator. When your rational expression is bottom heavy like this, higher degree on the bottom, then the limit is 0. So that's one of your rules, your shortcuts for limits of rational functions. You could also do L'Hopital's rule. So here, let me write out. If I had expanded, if I had multiplied out that denominator, this would be n plus 2 over n squared plus n. Technically has the form infinity over infinity. If I apply L'Hopital's rule, it's 1 over 2n plus 1. That definitely approaches 0. Okay, so the limit's 0. The other bit, I don't want to get too buried trying to prove this to you, but we have to prove that it's a decreasing sequence, or that the terms are decreasing. So an plus 1 is always less than an. One way to do that, if you like, would be to write this as a function of x plus 2 over x squared plus x. If I take the form like what I wrote over here, take the derivative of that and show that the derivative is always negative when x is greater than or equal to 1. That's one way to prove this condition here. Or just if you consider the fact that, so the denominator is going to increase more, if we add 1 to n, denominator is going to increase more than the numerator, so the fraction is going to get smaller when you have these bottom heavy functions. So yes, this is a decreasing sequence. Another way to look at this is if you take the reciprocal and you can convince yourself that's an increasing function, then the reciprocal would be decreasing. But so this series does satisfy the two conditions for alternating series test, so it converges. But we can't show it by the ratio test, was my main point for bringing it up. Okay, so I'm going to get rid of this. What about that second series over there? So in example B there, I do see a factorial, so ratio test is probably the way to go. So if I'm working B here, I'm going to do the ratio test. So I'm going to take the limit as n approaches infinity of the absolute value of the n plus 1 term over the nth term. And so that's the limit as n approaches infinity of, okay, so let's take some shortcuts based on things that I've told you. If it's going inside an absolute value, we don't need to mess with negative 1 to the n. The absolute value is just going to be 1, which, okay, fine. 1 times everything else. I can just drop that. This is always positive. This is always positive. So we don't really need to write the absolute value as long as we drop this negative 1 to the n. The an plus 1 term, so we write that out, that'll be 2 to the 4 times n plus 1 over 2 times n plus 1. Remember, you replace all of your n's with n plus 1's when you're writing out your n plus 1 term. So 2 times n plus 1 plus 1, factorial. There's your an plus 1 term. And then instead of dividing by an, I'm going to go ahead and multiply by the reciprocal. So times what I see here, but reciprocal. So 2n plus 1 factorial over 2 to the 4n. That's okay with you guys. Okay, so we need to write this out. So this is 2 to the 4n plus 4. I'm just distributing the 4 here. Times 2n plus 1 factorial over, if I distribute the 2 here, that's 2n plus 2 plus 1. So 2n plus 3 factorial, 2 to the 4n. Okay. Now, 2 to the 4n, this is a common factor, so I can cancel the 4n power here, and I'm left with 2 to the 4th. Now I also want to simplify the ratio of these two factorial expressions. So limit as n approaches infinity of 2 to the 4th, which is 16, you could write that if you want instead, times, so with the ratio of these two factorial expressions, you leave the smaller factorial alone. So I'm going to leave the 2n plus 1 factorial alone. And I'm going to take this, it's too bad it's at the very bottom. So this is a step to be careful with. I'm going to take this 2n plus 3 factorial and expand it downwards. So what I mean there is I'm going to start at the highest value, so 2n plus 3. The factorial would be 2n plus 3 times the integer that comes right before it. So just take one away to get the integer that comes right before 2n plus 3. If you take one away, that's 2n plus 2. Okay, I'm still not matching the numerator there, so I'm going to take one away again. That would be 2n plus 1. And there we go. So we would write 2n plus 1 factorial. That covers all the product of all the integers all the way back down to 1. So I can cancel the 2n plus 1 factorial. These minus 1s were just a little note to figure out the next term in this product. So I'm going to get rid of that before it confuses anybody. And so now you've got 16 over infinity. This denominator is approaching infinity. The numerator now is just a constant. So whenever you have just a number over denominators increasing without bound, then that ratio is approaching 0. Any limit of this form approaches 0, which is less than 1. So ratio test says that that series, for example, B, converges. And it's always important to say how you know.